All right, here's question 5 from 2014. It has a table. This table's a little bit different, though. The table's kind of going through and giving you different values for two different functions, f and g, and their derivatives. So question 5, part A, wanted to know what would be the minimum of f, so we're not going to worry about the bottom two lines with g, from -2 to 3. So the first thing I was thinking was, in order to have a minimum, we have to have a place where we have a zero derivative or an undefined derivative. So our two possibilities are at -1, because that has a zero derivative for f, and at +1. The next thing I want to check is, how does the sign change? Because that will determine if it's a minimum, a maximum, or nothing at all. So if you look at -1, prior to -1, you have a negative derivative, so it'd be decreasing. After -1, you're still negative, so you're still decreasing. So we would say that this is a critical value, but it is not an extremum. If you go over to +1, prior to +1, you have a negative derivative. After 1, you have a positive derivative. So you think about it's going down, decreasing, and then starts increasing. That creates a minimum. So the way you should write that, here's my work. I wrote kind of the two different possibilities. So here are the two places where the derivative is 0, and then the one that ended up being a minimum was 1, and I wrote that it's because the derivative is less than 0 between -1 and 1, but greater than 0 between 1 and 3. You could also, they wrote it real simply and just said how it changed signs. And they said that the derivative changed from negative to positive there. So therefore, it's a minimum. So any way that you can explain that sign change at 1 would be enough to get the point. As you can see, it was only 1 point. Part B wanted to know why there has to be a value where the second derivative of f would have to equal 0. Anytime they're asking about a derivative having to equal something in an interval, it's usually a mean value theorem. Mean value theorem says that there is a place where f prime equals f of b minus f of a over b minus a. Or in other words, the slope of the tangent line equals the slope of the secant line. So what this means is, if we use, so your f double prime equaling 0, that means f prime, there would have to be a place where f prime of b minus f prime of a equals b minus a. So what I did, first I want to explain that I can use the mean value theorem, and really the only conditions to be able to use it is you have to have a continuous differentiable function. And they tell you that it's twice differentiable, meaning not only is its derivative true, but same with the second derivative, basically like saying all those layers are continuous and differentiable. So my mean value theorem would say that you could take f prime of 1 minus f prime of -1 over 1 minus -1. And when you do that, that's coming from the table. You get 0 minus 0 over 2, which is 0, which means there has to be some place where the second derivative would also equal 0. If the slope of the secant line would have to in some way equal the slope of the tangent line. Now, because you are looking at an f double prime, that's why you have to use the single primes in your mean value theorem. So for their scoring, the expectation was, again, you should say that it's differentiable, so it's continuous, and you can be real simple with how you say that, and then show that work equals 0, and therefore the mean value theorem says there has to be a place where it happens. If you get 1 point for showing that you realize that you need to do an f prime of 1 minus an f prime of -1, and that you get 0. And then the second point is kind of that explanation. Are you using the theorem? Do you understand why you can use the theorem? Part C wanted to know, they have this h function, which is defined as the natural log of another function, so kind of a generic piece here, and it wanted h prime of 3 and then show your work to how you get it. So this is a generic derivative, or kind of like a semi-generic derivative. You're deriving a natural log. So the way you derive a natural log, and I wrote that down first when I did this, let me get to mine. I wrote off to the side, the derivative of a natural log is du over u. It's the derivative of what you're taking the natural log of divided by that. So the derivative of natural log of f of x would be f prime of x over f of x. So this is the derivative, this is the original. You're putting 3 in, so it will be f prime of 3 over f of 3. You're going to your table, and these were values that you could find in your table. F prime of 3 was a half, f of 3 was 7, 1/2 divided by 7 is 1/14. And they scored it, I think they did 2. Oh, they did 3 points. They did 2 points for the derivative, which to me was pretty generous because it's actually, it looks awful, but it's a pretty easy derivative to find, just that du over u. And then 1 point for your answer of 1/14. And then finally, part D, I thought part D might have been the toughest part just because of how it looks. It's asking you to do an integral. It has boundaries for your integral, and your integral is kind of a mess. It has this f prime of g of x times g prime of x, When you have something like this where you have these like composite pieces, this is an example of U sub. U is going to be that inner piece, the piece that's having something done to it, and then du needs to be there. We need to check for adjustments. So that's the first thing I wrote down, and then I'll scroll down and show you what I finished doing. So I wrote that U would have to be this inner function g of x. The derivative of g of x is g prime of x, which you have. So you actually have no adjustment here. So let me go down to my actual work here. So I kind of did that again here. My u is my inner function. My du is g prime, which I have. And again, I just kind of wrote down, this is a very generic u sub. When I write it, what I end up having is I'm integrating f prime of just u du, where we call this inner function just generically a u. The integral of f prime is f. So when I integrate f prime, I just get f of u. So then I'm going to put my g of x back in, kind of like I use the u and then I get rid of it. And I am done integrating and I'm ready to put my boundaries in, top minus bottom. So here's my work with my boundaries. F of g of 3 minus f of g of negative 2. You again have to reference the table a lot. G of 3 going back to that table was 1. So you have f of 1. G of negative 2 going back to the table was negative 1. So you get f of 1 minus f of negative 1. Make sure you're reading the table right. You get 2 minus 8, which is negative 6. I think their work was pretty similar to mine. This was probably a little neater. They didn't show as much work. I actually wanted to write down what's the u, what's the du, how does it work when you integrate it. They kind of went straight to when you integrate it, you get f of g of x. This is kind of a very long way to write a generic u sub. And then they put their boundaries in and did what I did. They gave 2 points for the fundamental theorem, essentially realizing that you understand how to integrate it, even though I think a lot of it's kind of done behind the scenes, and you realize when you integrate an f prime, you get an original f, and that you know how to put the boundaries in. And then your last point is really the computation, and it's a lot of just reading the table correctly. So that's how you get 9 points on number 5. I thought there were a couple little confusing pieces to this, but it also had a good mix of derivatives and integrals and rules from a lot of chapter 2, 3, and 4 again is really the focus here. So go ahead and tabulate what you got on this one. We have one more that I'll have a video to explain. And then at that point, I'm going to ask for a score report. Thanks, guys.